Now let's focus our discussion on binary heap. Binary heap is a binary tree, not a search tree. Binary heap is a binary tree and which is also a balanced tree. So in this video we will look at what are different operations that can be performed on a binary heap, how insertion, how deletion operations can be performed on a binary heap. And we will discuss few applications also. So binary heap is a data structure and it is actually a complete tree. So binary heap is a binary tree and it is a complete tree. So the definition of complete tree is given here. All the levels are completely filled except possibly the last level, and the last level has all keys as left as possible. So we can look at an example here. Suppose that I have only one node. So this one node actually preserve the property of a binary heap because this level 1 is actually filled. This level 1 is actually filled. Now suppose that if I insert another node, then we can see that we have two levels and the last level is level 1. So this is my level 0 and this is my level 1, and we will have several levels below this one. Now this is also a complete tree. Now if I draw another route here, this also makes a complete tree. And if you want to insert another node, you will be inserting the next node here. So this is also a complete tree. Now suppose that if you are going to insert another node here, so this violates the property of a complete tree. The reason is because we could have possibly inserted the node here instead of inserting at this point. So the definition says that all levels except the last level. So here the last level is this one, level 2, and all keys of the last level should be as left as possible. So it should have been here rather than at this point. So this one is not a complete tree. So if you redraw this node at this point, this makes the tree a complete tree because the last level is there and all the nodes in the last level is as left as possible in this case. Now suppose that if I insert at this point, is that a complete tree? The answer is no. It should be at this point to make this tree a complete tree. The next one should be at this one. Suppose that if I insert another node here, this is also a complete tree. And what about if I insert at this point? No, because we have the last level at this point and the previous levels are not completely filled. So this is not a complete tree. So this is the concept of a complete tree. So whenever you find a binary heap, it will be a complete tree and the insertion will be happening in order. First the root, then left, then right, then we will select the left child of the root, then we will fill its left and its right, the next child's left, next child right. This is how the insertion goes on. Now this property of a binary heap will makes them suitable to be stored in an array, which means that suppose that I have certain elements here. Let's say the first element is A and the another element is B, the element here is C, then I have D, E, F and G. So we can actually use an array data structure in computer to store the data of a binary heap. So suppose that I have an array which has some certain number of spaces. The first element, if you are going to insert, it will be inserted at the first position. The next element will be here, the next element will be at this position, then D, then E, then F, then G, and we can also have some other spaces reserved to store the next coming data. Okay, now so this element has certain indices 0, 1, 2, 3, 4, 5 and 6. Now a binary heap, I'm going to look at the next point. A binary heap is either a min heap or a max heap. In a min heap, the key at the root must be minimum among all the keys present in the entire binary heap. The same property must be recursively true for all nodes in the binary tree or in the binary heap, to be specific. And max heap is similar to min heap. So we can actually have two kind of heaps. One is min heap, another one is max heap. So I will quickly look at what this actually is all about. So if you have a min heap, so first discussing min heap. Okay, if you have a min heap, the property that we need to preserve is the root should be the minimum element in the entire binary heap. So if the root value is 2, then whatever comes below 2 should always be greater than 2. So I can have a value 4 here, that is allowed. Then I can have a value 9 here, that is also allowed. Then if you want to insert another number, suppose that I am inserting a number 12, that is allowed. And if you are going to insert the next number, it should be on the right side of 4. We are not going to compare with any of the value. We are just going to look at whether the number is greater than or less than the number of its root. So here I can have the number let's say 11, and here I can have the number 20. So this one is an example for a min heap. The only thing that we need to look at is, if you have a key at the root, all the numbers following the root or below the root should be always greater than the value at the root, or in other words, the value at the root should be the smallest among all the subtrees of the binary heap. Now if you look at this 4, the 4 has value here, and all its child or the descendant of 4 has a value which is greater than 4. And if you look at this number 9, the 9 has only, then value 9 is less than the value 11 as well as the number 20. Then I can have another number here, let's say I'm inserting a number 13, this is also allowed. And then I can insert a number here, let's say not at this point. I can insert another number here, let's say that is 17, that is also allowed. The only thing that we need to preserve is, if there is an element, then its root should be minimum less than the value at this number, that is the value 4 should be less than 12. So this is the case of a min heap. Now if you take an example of a max heap. If you take an example of a max heap, then the example of a max heap is the value at the root should be the largest among all the values present in the entire data structure or entire binary heap. So if you have 100 here, you can possibly have 50 here, and you can have 30 here. We are not looking at whether the 50 should come on the right side or 30 should be on the left side. There is no such restrictions for binary heap. The only restriction that we need to impose is, if it is a max heap, then the root should be the maximum value compared to its descendants. Now if you have few more nodes here, then I can fill this value with a value, let's say 40, which is possible. Then I can have a value here, let's say 20, that is also possible. I can have a value here 10, that is possible. I can have a value here 2, that is also possible. Though we are just looking at the root and whether the descendants are less than the value of, in this case less than the value of root, then this is also a binary heap, or specifically saying it's a max heap. So these are two different classes of heaps. Now if you try to represent these nodes, these values in an array, then the structure of the array will be like this. So first I will have value 2, then I will have the value 4, then I will have value 9, then 12, then 5, 11, 20, 13, then I have the number 70. In this case it will be in this case it will be 100 first, then I have 50, then I have 30, then 40, then 20, 10 and 2. So this is how we can represent the numbers of a binary heap in an array. Now we have to discuss few important properties of binary heap when it is represented in an array. So I am writing the indices here 5, 6, 7, 8. Now let's see the first property. If I is the index of an element in a binary heap, then the index of its parent is, here it is the floor of I minus 1 by 2. So let's see. So if you have the index of an any element, its parent's element will be I minus 1 by 2. Parent's index will be I minus 1 by 2. Suppose let's take the example of the number 11. If you want to find the parent of the number 11, what you have to do is you take the number 5, then subtract 1, then you divide it by 2, then you will get the number. So here it is 4 by 2, then you take the number 2, then you find the integer value which is less than or equal to the given number. So the integer value less than or equal to 2 is 2 itself. That means that if you want to find the parent of 11, that will be at the index 2. So if you look at here, that is the number 9 is the parent of 11. So this has index 5 and this has index 2. That is true. Now if you look at the number 17, though if you want to find the parent of 17, the index of 17 is 8. So you do the same operation, that is 8 minus 1 by 2. 8 minus 1 by 2 is 7 by 2, which is equal to 3.5. Then you find the floor, that is this lowest integer less than the highest integer less than or equal to the given number. So 3.5 is a fraction. The lowest integer near to 3.5 is 3. So if you want to find the parent of a number at the position 8, then its parent will be residing at the index 3. So you can see that the parent of 17 is 12, which is at an index 3, and this number is at index 8. So this is the first property, and that the same applies for a max heap also. And we will be continuing our discussion only on min heap. The same kind of algorithm can be extended to max heaps as well. Now the second property is, if I is the index of an element in a binary heap, then the index of its left child is 2 into I plus 1. That is, if you have a element, if you have a number and you know the index of that number as I, and if you want to find the left child or if you want to find the right child, you can use these two equations. If you want to find the left child, it is 2 into I plus 1. If you want to find the right child, it is 2 into I plus 2. So let's look that also in this particular example, or otherwise I will use this heap to find it. Suppose that 100 is the root which has an index 0. Now if you want to find the parent, sorry, the left child, then you have to find 2 into I plus 1. So in this case I is 0, 2 into 0 plus 1 equal to 1. So the left child of 100 is at index 1. And if you want to find the index of the right child, you do the same operation, except the fact that instead of plus 1 you use plus 2. So this will be 2, this is actually multiplication, 2 into I is 0 plus 2, which is equal to 2. So this number is at 2. Now if you have this number 30, and if the 30 has an index, let me write it here, 0, 1, 2, 3, 4, 5 and 6. So the 30 has an index 2. and you want to find the left and right child index of this number 30. So the index is 2, so the left child will be at 2 into 2 plus 1, which is equal to 5, and the right child will be at 2 into 2 plus 2, which is equal to 6. So you can see that the children of 30 are at the indices 5 and 6 respectively. So these are the few important properties of binary heap, and we will be focusing our discussion only on min heap from this point onwards. Thank you very much.